Good morning. I'm Kurt Wilson, Vice President of Engineering here at Delta Tau, one of the overall designers of the Power PMAC, and I'm going to be giving you the introduction to the Power PMAC class. I've given you the handouts for this. This is kind of a separate introductory thing to give you an overview. Everything that I cover, we will be covering in more detail with the other instructors. But I want to give you kind of the overall flavor for what's going before you get into detail on certain things. And you will be getting the handouts to the bulk of the material in about an hour. So without further ado, we'll get going. Okay, so what is Power PMAC? I know several of you have used earlier versions of the PMAC. What distinguishes Power PMAC is it is a general purpose embedded computer rather than a specific application. You can, and a few people are using it for applications that have nothing to do with motion control. Okay? But we have a built-in software application that's dedicated for motion and machine control, and the vast majority of Power PMAC customers use that heavily. But it is kind of on a spectrum from the people who don't use it as a general-purpose computer at all, and to the people who use it almost completely as a general-purpose real-time computer. With our software application, we have a script language that's optimized for this type of control. It has sequenced motion programs, automatically sequencing, which general purpose languages like C do not do well at all. And asynchronous PLC programs can run in the script as well, although more people tend to do that type of functionality in C. And automatically under the hood, it's executing the motor servo and phase commutation algorithms. In addition, we have a wide variety of machine interface circuitry, including servo interfaces both of analog and digital form, analog and digital commands, analog and digital feedback. Also general purpose I/O in both analog and digital forms. We have a bunch of industrial network interfaces like our own macro, and EtherCAT is also getting very popular. And then field bus interfaces some customers use for things like DeviceNet is one of the popular American ones, Profibus is popular in Europe, CC-Link is popular in Japan, and several others as well. The Power PMAC CPU, we've been using the Power PC family of processors, although it's also amenable to be compiled on others like ARM or the x86. It is in both, we have both single core and dual core configurations. The full 32-bit short word, 64-bit long word architecture. If you've used the older PMACs, those are 24 short word, 48 long word. This gives increased resolution and range. The floating point math is done in hardware, which makes it much faster. The older PMACs were fixed point, and we had to execute the floating point in a software library that results in very high-speed calculations, and this 10x over turbo is very conservative for the real math, and a huge dynamic range and resolution. We haven't seen anybody come close to kind of range or resolution problems they had in earlier controllers, although it was a small percentage of customers ran into it, but a few did. The memory is much larger. Gigabytes of active memory, and we have error correction on them. Built-in NOR flash for our stuff, built-in NAND flash for your settings, your programs, tables, things like that. You can install also external memory, whether just to load it on USB stick or camera card, or you can have it in there permanently if you want more capacity. And a lot of people will put in large cards or stuff to say store experimental data is pretty common. Built-in Ethernet, 100 megabit or 1 gigabit interfaces. That's the main interface to the host computer. So here, there's just an Ethernet interface from your PC on your thing to your demo box. And there's USB 2.0, client and server, both there. There's even an old RS-232. The streaming nature of the Ethernet makes it much, much faster than it was in the older PMACs. With direct memory access, direct connection. It is possible to have the Power PMAC do a video interface as well, if that's what you want. This is a block diagram really for your future reference showing the core computational engine of the Power PMAC, starting with the processor, the active RAM, and the links to the flash, the core boot flash, and through these devices to the NAND flash, internal or external, the communications link, and then the link, our internal link, we call it the U-bus, universal bus, that in your thing is the backplane from the CPU card to the servo and I/O interface boards. So that's the basic idea of what we can do. We have optional PCI Express for various other types of interfaces that can be commercially bought and hooked in. Okay, the operating environment. We have a full real-time operating system based on Linux, where we've added a hard real-time kernel. Plain vanilla Linux is multitasking like Windows is, but also like Windows, it is not hard real-time. And while going through for many tasks, it's fine to have it just cyclic. That is not suitable for real-time control, for servo kind of thing. There must be a very well-defined latency for this type of motion control. Otherwise, you get servo hiccups from missing a beat, and that can destroy things. So the hard real-time tasks operate on interrupts. The phase interrupt, if we're doing commutation or current loop, that's default 9 kilohertz. The servo interrupt, where we do the interpolation to compute the new set points, desired positions, close the position and velocity loops. All done on interrupt. What we call the real-time interrupt, where our motion programs are executing, and the foreground PLCs. If you have these types of tasks, asynchronous to the motion, but you want them to operate at a high priority. We do even have capture compare with the newest ASIC, a hardware position capture event or a hardware position compare event can interrupt the processor at the highest priority, really for updating to or from a list. It's higher priority than servo and phase, so you have to be very careful with it. But it has proved very valuable for a certain class of information where these happen at a high frequency. Other tasks are operating in the general purpose operating system, like our background PLC programs, some of the status updates, command processing, and then independent applications that you can write operating in background. And these all background and foreground tasks operate through a shared memory interface. Everybody has access to pretty much everything. Many environments separate those out. We combine them into a single shared memory. You have full file management system. Just like a regular computer, the programs and tables, gathered data can be stored and transmitted as files using the standard Linux type things. We have the hardware configurations. What we call the UMAC is the rack that I think all of you have. There are a couple, yeah, nobody's using any of the others. So, so UMAC, where you have a CPU card, you have a power supply, and you build up as you want with the different interface cards, servo interface, general purpose I/O, field bus, network, things like that. A more compact version we call the Etherlite, just has a CPU board and a network interface, macro and or EtherCAT, with an optional field bus. But this is where you are not, all the wiring is really remote. None of the field wiring goes directly into this. It goes to nodes on the network, remote nodes on the network. Particularly good for large systems. We have the brick combined controller amplifiers that are being very popular. We sell them in this integrated box. For those of you on the labs, they're kind of in a rack-mounted, 19-inch rack-mounted version, kind of flipped on its side for the scientific type applications. But the key is the controller is in there and the power circuitry, the amplifier. We have an AC version up to 240 volts AC input, rectified to about 350 DC, and then what we call the LV version, up to 60 volts DC input, and for good optimized for 2- and 3-phase motors, the two-phase steppers or 3-phase servos. In the UMAC, we have accessories. I mentioned the various interface boards that you could put in modularly. This shows it without the front plate. Here's the side view with the front plate. But these are what are called 3U. That's 3U Euro cards, 100 by 160 millimeters, sliding into the rack. There's a backplane connector over which they talk to the processor. So servo, digital and analog I/O, network and field bus, power supplies in there as well. For developing your application, we have a PC application called the Integrated Development Environment. Brings in many standard software development things and also aspects that are unique to the PMAC. Many status screens for things like position, motor status bits, what we call a watch window where we'll repeatedly query whatever variable of interest to you. I use it all the time. Terminal, so you can talk to it as if it were a dumb terminal, which is still very useful for issuing commands interactively, particularly in development. Editor, smart editors with debugging, IntelliSense, all these kinds of things. Tuning and plotting screens that you haven't seen yet, but you will. You can incorporate the individual windows into your HMI. We build it around Microsoft Visual Studio. If you buy a Microsoft Visual Studio license from Microsoft, you can then take these controls and integrate them into your application, customizing the look and feel of them for you. But it gets a lot of people started very quickly on an HMI. The script language that we have, again, optimized for motion and machine control. It does many things well that a standard high-level language does not do, particularly for people who aren't software experts. People who really know C, they'll do a lot. They probably will do a lot of things in C. People who don't, this can get them going quicker. One of the things that does automatic type matching of different variable formats. You can combine anything from a Boolean single bit to a 64-bit floating point in a single expression without recasting, without worrying about the type matching. And since we use all these kinds of things in an application, single bit I/O to integer feedback to double precision floating point, people who are not software experts can drown in the type matching. So this handles it all together. The motion programs particularly, we call them synchronous. They're sequenced by the move. One of the things that commanding a move does is it takes a finite amount of time rather than just, say, turning on an output where you just do it and goes, but it may be a 10-second long move. And standard high-level language, you at the application have to monitor for it to be over. And particularly when you have a sequence of moves together, you've got to be calculating ahead, and it gets to be very complicated. We've put that stuff all under the hood, so you don't have to worry about it in our script language. The pipeline can get 7 stages deep, and it'd be tremendously difficult to do by yourself. So we sequence it move by move. The PLC programs, on the other hand, are free running. Much more like what you're used to with a standard high-level language, and a lot higher percentage of our users do these types of functions in C rather than script, although you're still welcome to do them in script. Okay? It's easier to access the machine I/O points. Easy to declare a Boolean within a word, things like that. So you don't have to do sort of the masking and shifting to get at a single I/O point. The script engine will do it for you. The math and logic in Power PMAC are like C. If variable equal something, that's different from the older Turbo PMAC where it was based on the old BASIC language. So more power and flexibility. We do have built-in debugging features like breakpoints, cycle points, single step available to you that we didn't in older languages. Just kind of an overview of the script language. Got a lot of the functionality in there. Dozens of mathematical functions. Trig functions can be in radians or degrees, random number generators, math and logic operators, many kinds of things, array access to numbered variable types, vector and matrix operations that are very fast in there, logical while loops, if-else branching, and the switch. Many people had requested this, the case statement, that we didn't have in the older ones. Subroutines with stack variable calling, real variable calling within motion and PLC programs. We've added built-in data structures, and this is the main technique for your access to the key Power PMAC registers. They will largely replace, if you've used the Turbo, the old I and M variable use. And these cover both hardware and software registers, control and status, with giving them English language names that are useful. Key setup elements are saved to flash memory, as always, so they come up every time automatically. These are available from both script and C programs. They're automatically included for your C programs with the proper header file. And we have an IntelliSense. So if you're not sure exactly what the name is, was it jog speed or jog velocity? It's jog speed that I want, because it'll come up as you start typing here. And we have the major structures. Sys is for global, motor, coordinate system, the ASICs, which we call gates because they're gate array technology, comp tables. Basically, everything's built within a structure. When we have multiple, say, motors, coordinate systems, you have an integer index for them. Okay? You can substitute your own name for the structure if you want a shorter name. And you can define a pointer with a name also to a pointer variable to a structure as well. To run the C code, we have the GNU cross compiler. It's public domain, open source. We haven't monkeyed with it, but we've incorporated it into the IDE. You can use it for code for both real time, such as custom servo algorithms, non-real time tasks there. We can use automatically generated C code. It's quite popular to use MATLAB Simulink to generate an algorithm. Often in the universities, they love doing custom servo algorithms. In the field, we see all sorts of other uses for this as well. It's automatic. It automatically generates the C code that we can compile and load into the PMAC. Again, we supply the header files that give you access to our key registers, our data structures. Remember, in script, our language is not case sensitive. So accessing something like jog speed, it doesn't matter the case of it. In C, the C rule is that you must match the case properly. We can't change that. And we have a supplied API, application programming interface, to give you access from C to functions like command to jog, start a program, abort, things like that. Or we have function calls that you can do from C. Okay, the motor calculations compared to the old turbo PMAC, these are all done in floating point math. All the trajectory, servo, phase commutation, and this lets us do more complex algorithms than we did in the turbo without adding, well, it's known as quantization noise. Turns out that in servo control, the things you do to stabilize the system, give it phase lead, multiply up the quantization. The less resolution you have, the more problem that is. Here we've thrown so much resolution at it that we've basically driven that problem down. So I mentioned that you really never run into rollover or saturation concerns. It allows our registers, position, time to have meaningful units, no strange fractions of a unit, just whatever units you want. And it's still faster than the fastest Power PMAC. And this also gives you increased flexibility to add custom algorithms. We can control up to 256 motors from a single CPU. Coordinate systems are our structure for grouping together motors that you want to act in a coordinated fashion. Hopefully it's obvious. If you want motors to go in a completely coordinated fashion, starting, stopping, changing speed at the same time, you put them in the same coordinate system. If you want independent operation, you put them in separate coordinate systems. And we can have up to 128 independent coordinate systems and up to 32 independent axes per coordinate system. The names, we kept the 9 single letter names that we had in the older PMAC, added 23 of the 26 double letter. So if you have more than 9 in a coordinate system, you can start using the double letters as you want. And 2, what we call Cartesian axis sets, 3D with some spatial things. You can do circular interpolation on any plane within a 3D space. X, Y, Y, Z, even a slanted plane as you want. We can assign motors to a coordinate system in 2 ways with a simple. One is with the simple axis definition. Motor 1 is assigned to the x-axis in a coordinate system with, say, a scale factor. That's the simplest and probably the most common thing. If you have a complex geometry with interrelations of how the joints, the actuators, contribute to the tool end position, which is getting more and more common, you can define them in forward and inverse kinematic subroutines. Again, we'll be covering all that. So here, shoulder, elbow have a trigonometric relationship to get the x and y position here. And we can now do real-time reporting of the axis data position. What is x and y? It will read the motor positions and compute the axis position as needed for reporting. This makes it much simpler than it was in the older PMACs. We have some sophisticated motion trajectories. All the move modes of the older PMAC are still supported, but we've enhanced all of the modes. Fundamentally, three classes. One we call the point-to-point mode, traditional blended, and the modern spline or contouring. The point-to-point mode is the jog moves for the motor, the homing search, and in the program it's rapid mode, sort of minimum time point-to-point move given the constraints. We can also alter the destination in the middle of a move based on either a new command or a trigger input that we've done, like the home trigger for a homing search move. We've added jerk. Jerk is the derivative of acceleration, so yet the third derivative of position added, and the ability to alter destination at up to the servo rate. We've done perfect circles by commanding the tangent every servo cycle, just to test it. The traditional blended moves, linear interpolation and circular interpolation, we have improved them, given them more flexibility. Everything has floating point resolution, things like that. We can have separate acceleration, deceleration rates or times, and better optimized look-ahead calculations to keep you out of trouble from, say, a sharp corner. And the modern spline and contouring modes we call PVT, position, velocity, time, and the spline mode in there. So all of these things are available, and you'll be commanding moves in them shortly. The PLC program enhancements compared to the old ones, I know many of you are using the old ones. You can now do subroutine, subprogram calls. You can command axis motion directly from a PLC. Rapid mode moves only. Now here, the program execution does not pause like in a motion program. It's not sequenced by the move. So if you command a move from the PLC, the software logic keeps going. It can be very valuable in certain kinds of things because a few milliseconds later, you'll be coming down again, evaluating conditions, and maybe you can stop it or change direction. Here, some people prefer this method of programming. If it's really, I'm going to start a move and maybe change it, I've got to make up my mind what I want to do, it's often better commanded from a PLC program. We have what we call direct motor and coordinate system commands. In older PMACs, you had to use the command quote and put it in quotes and pass it through a parser. It was inefficient. Here we can do it directly. It's simpler and stuff. And improved debugging features with cycle counters, breakpoint, and even the single-step capability for a PLC program. A new ASIC, you don't have to use it, but a new ASIC has the next generation. It's one of these faster, better kinds of things. All the features involved, higher resolution, higher speed, does many of the things that used to have to be done in software computation as far as processing I/O. The speeds are 2.5 times faster, which gives you 1.5 bits extra resolution. I'm not going to go too much into detail. We'll cover those a bit later. But you can use this, and it does have the interrupt capability for what we call the position capture and compare events. This I will set up, leave for you. This was some benchmarking we did early on. We don't even have the faster versions of the Power PMAC in there, but showing what the standard turbo PMAC, the fastest turbo PMAC did for various tasks, and then actually the very early prototype, but the standard Power PMAC that you can see it's significantly faster than even the fastest one and for phase and servo, and this is even with floating point versus fixed point. Things like the custom servo is where it really went up, really improved. Here was a particular application that took over 300 microseconds to do, and it's brought down to between 1 and 2 microseconds here. And even the kind of things in the script language that you do brought down by well over an order of magnitude for most of these events, both computation and Ethernet transfer. So one of the things you get is a significant improvement in speed. Another thing, increased hardware and software sophistication, which is probably what many of you will be interested in.